This afternoon's Brew and View presentation is sponsored by Proto Labs. It's going to be a presentation on designing for direct metal laser sintering. Greg Thompson, who's the global product manager for 3D printing, is going to do about 30 to 40 minutes on this presentation. At the end, we'll have a Q&A, and we'll go around with a microphone, and you guys can ask questions. So with that, please welcome Greg Thompson to the stage.
All right, thanks. Can everybody hear me? All right. Now we can't hear me? Now we can? All right, maybe the belt mic isn't working. We'll just use the podium. Get double feed. So yeah, I'm the global product manager for 3D printing at Proto Labs, and I want to actually pause and thank David Bentley, who's the process engineer for metals printing. You know, it's a lot of his work. We're going to show you a lot of test builds that we did. We really designed this for folks that may be familiar with 3D printing and it's not as much in the metals. Metals obviously is a big emerging space. There's a lot of intrigue about it, but it tends to be a little bit of a longer and possibly more expensive process. And so it's really critical to understand what your design goals that you're looking to achieve and how to optimize parts for this process with the design. And so that's kind of what we've geared this whole presentation to you for. We'll get right into it. A little bit about Proto Labs and what we do. So we're a fully digital on-demand manufacturer. So we have a CNC machining and injection molding and a 3D printing business. And so a lot of our expertise comes from setting up and building and supporting millions, literally millions of parts every year. We have 3 different 3D printing technologies that we support. We've got 2 in the hard plastics in stereolithography and SLS. We've got elastomers with the polyjet, and then obviously the metals printing. So let's get into it with metals, and let me start actually with addressing kind of how the process works, and begin with the name. So direct metal laser sintering, a bit of a misnomer, right? Sintering typically is a process that uses either heat or pressure, right, to fuse or sinter parts, but it typically does not achieve a full melt. Well, DMLS does achieve a full melt, and so you'll also hear this referred to as either selective laser melting or direct metal laser melting. So slightly different than electronic beam or E-beam. All of the DMLS, DMLM, or SLM, they really do achieve a full melt. So the process itself is a little bit easier to explain, and it's a 3D layer, or it's a 3D printing process. So like any other 3D process, it's layer by layer. And so we take the file of the part and slice it up into numerous layers. We then use a laser, high-powered laser, to melt each section of the part within that layer, and then we'll move on. So as you look at the diagram, the way that it works, these are relatively large machines because they're multi-chamber machines. So the chamber on the left is what we call the dose chamber. That's where all the powder is. Now the powder itself is pure powder. So if we're using a titanium powder, this is a powder that has been derived from melted and then atomized titanium. So as we'll get into it and show you some of the characteristics of it, you can achieve nearly dense parts with wrought properties. So these are pure alloys, engineering grade alloys, depending on which you're using. So the powder itself starts on the left in the dose chamber. The laser, as you can see, is powered and guided by a galvo system to melt that layer file. And then once it's completed that, the build chamber, which is the one in the middle, will go down in an elevator-based system based on whatever layer thickness that you're using, and it will repeat that layer by layer. Now, between the layers, there's a blade that passes over, and the chamber on the far right is really just a capture chamber for any of the excess powder. So that's kind of how the process works at a very high level for those that aren't necessarily familiar with it. Now, the process really, at its core, when you're hitting it with the laser and you are achieving that melt, it really is, in essence, a micro welding process. And so what we're showing here on this image is 100-time magnification of our 316. So we built a cube, potted it up, and threw it under a microscope, and you can see all the different layers that are in there. So the basically the weld beads that exist throughout the part at 100 times magnification. Now, this is something that we do with most of our parts. Periodically testing just to make sure that we're getting the density that we like to achieve, the consistency that we like to achieve. But just to give you guys a view, like this is what a part looks like when you cut it open and you magnify it up. Now we do have 6 different alloys that we tend to work with. They're fairly common. Aluminum probably being the most challenging just how it melts and operates, but we also have cobalt chrome. We use some of the Inconel, some of the nickel-based alloys, 2 different stainless steels, and titanium. And as you look at the tensile, yield, and the hardness, you'll see they're very, very similar to what the raw properties would be or what you would expect them to be in other processes of manufacturing. So you can really achieve engineering grade properties out of the DMLS process. So why do people use DMLS? Because it's really important to focus and achieve at least 1 or 2 of these design goals. And so the first is reduction of components. So you probably have all heard of the GE LEAP fuel nozzle that took 30-some components and prints it into a single part. Now, there's a lot of advantages when you come in reducing components. Now, the first of which obviously is you've taken out assembly steps further down in your manufacturing process. So you've removed assembly, that's reducing labor. So there's a lot of advantages there. But if you think about printing components in one, you've also, in removing an assembly step, you've also removed a potential point of failure within the part. So oftentimes the parts can perform even better as a single part than they could as a multi-component assembly. Now, the other thing, there's a lot of soft costs that our customers are talking about when they're talking about reducing components. So every part that you've got, right? You've got to design, you've got to qualify, you've got to order, you've got to inventory, and you've got to manage, right? So there are a ton of paperwork and soft costs. And plus you've got additional suppliers within your supply chain that are providing parts in for your end project or part. So there's a lot of savings to be achieved in reducing the number of components. And so getting beyond sort of part level thinking into component level thinking, I think is going to be really critical over time. But if you're first getting into DMLS, there are some other sort of simpler part level goals that you can achieve. So one is reducing weight. Now this can save just material in and of itself. It can reduce the overall weight of the component. Oftentimes you're achieving this by literally removing material and printing it within a honeycomb or a lattice structure. So yes, that saves material in and of itself. But if you're in the automotive or the aerospace industry, where every ounce counts and there's thousands of dollars per ounce of fuel consumed, that is an advantage as well. The other thing you can do is optimize the performance of the part. So you can use a lot of organic structure and organic surfaces. So you're really free with design complexity in DMLS, like with any 3D printing. And so leveraging those can optimize the performance of your part as a whole, and it can reduce just basically overall cost. So it's fantastic. If you look at this part on the far right, that complexity essentially comes free of cost. So this is a part there is no way that you could really machine or mold that in any other fashion. It would be cost prohibitive, but you can achieve it in DMLS. So we mentioned a lot about DMLS and what the applications are and the advantages. A lot of the industries that are taking advantage of this, just to give you a sense, medical components, we can print at Proto Labs extremely small, intricate, complex parts. So you can see the surgical jaw there in the lower right of what we're able to achieve, usually on our smaller, higher resolution machines. We talked about conformal cooling, so you can use internal channels. And so we see that, yes, I've got an example later where it was regenerative cooling that was used in the aerospace industry. We've also seen people use that within their tools themselves. So if you've got a really high volume tool, internal channels to cool it and reduce the cycle time can unleash significant value and savings for you. And then we see a lot in electrical components, heat sinks. So you're able to increase the surface area on the heat sink and make it fit within really tight, intricate locations. So there's a lot of applications, within DMLS. Now, the answer in 3D printing, when we get asked things about what it can do or what what it's capable of, the right answer is always it depends. And so I'm going to go through a little bit of caveats and qualifiers here for a second. So we use concept laser equipment. So it depends on what type of equipment you're running in and what parameters you're running it on. So we use concept laser. So all of the test parts that you're seeing were produced on these machines. The M2 is the larger format machine. It can get up to about a 10-inch cubed part on it. we run that in 30 micron layers, so each layer is only 30 microns thick. The M-Lab is the smaller machine. We really use that for small, highly detailed parts. It has a build envelope of about 3 inches cubed, and we run that at 20 micron layers. So you can see some of the specifications we're able to achieve off of that equipment. So generally we talk about tolerances plus or minus 0.003 of an inch, plus a thou inch per inch, for larger parts. You're seeing there the, within the normal and the high res, what the layer thickness is and what a typical minimum feature size can be. So, we can achieve, with some conversations with you, we can achieve tighter than 3 thou, but generally for the average part, that's what we're achieving. So, before we get into the process, I want to reiterate that we're not design engineers, we don't have professional design services, but what we do have is all of that expertise in our engineering team of looking at, assessing, doing the support strategy and the build preparation for literally over 1 million parts in our history within 3D printing at Proto Labs. And so we can tell you kind of just by looking at a parts that have been similar in the past, we can provide that design for manufacturability feedback. And one of the things that we learned over and over again as customers have come to us with DMLS opportunities and asked us to look at these parts and evaluate them for them and provide some quotes and cost, we can tell you that it is not a replacement for traditional manufacturing. So if you look at these parts, I mean, you can kind of tell they're either a MIM part, right, or a sheet metal part, or they're a cast part. And we can tell you with pretty high confidence that if it can be machined, it probably should be machined. And if it can be molded, you probably should mold it. So if you're not leveraging DMLS to unlock either a new process or a distinctly new design for you, you're not going to achieve a lot of the value that 3D printing is capable of providing. So I want you to have that in your minds as we work through this. Because quite honestly, the parts that we're looking at on this slide, they'd be extremely cost prohibitive to build in DMLS compared to the traditional manufacturing. So a really quick case study that kind of highlights this. So this is Huge Design. They're a design firm. They were supporting one of their clients, Evo, and it's an urban utility bike. So it allows the rider to swap out components in the back end, be it a carrier or a basket or even a baby seat. And this was a concept bike, and that's actually another really good application for DMLS is really small volumes. So within prototyping, there's a good solution there as well. So the Evo, this concept bike, they were looking for ways to get some prototypes done, some functional prototypes, and they used DMLS. Now, as we spoke with them, we kind of evolved the concept with them a little bit. So really, they did a lot of the lugs and the foreground is where a lot of the work was at. So the lugs, they actually took multiple components and were able to print them into one. By doing that, they skipped this mitering step that they had to do, that they typically use during the frame assembly. And so they removed components out. They skipped an assembly step. The fork crown was probably more complex, and what we were able to do was use this really organic design that would have been nearly impossible to achieve any other way. But it allowed for the modification of the rear end to be achieved. So by using either complex design and reducing assembly, they were able to get the concept to market and for much cheaper than what they originally were intending to do. All right, so that's just a one little case study. So we've talked a lot about DMLS, and we've talked a lot about what the design goals would be. Now we're going to talk about some of the considerations of the process and the real-world implications that has, on your designs and your parts. So, as we all know, the days of thinking that you can print pretty much anything that you can put into CAD are kind of done, right? It's true. The printer will happily print away whatever you feed it in a CAD file, but you may not like the results that come out. And so we're going to look at how to properly design and how to set those expectations. So let's start with small features, right? We talked about 0.006 of an inch, and here, so DMLS is fantastic for really thin walls. You can achieve really thin walls. You can achieve really sharp features. As you can see, some of these medical equipment devices on the far right, that really intricate mesh, the lattice in the middle. So you can achieve features that are as small as 0.006 of an inch, and we do that regularly and repeatedly. But because of the rapid heating and cooling that's occurring in that melting process, there's a lot of stresses that are involved in this process. So not every feature can be 6/1000ths of an inch, and not every feature of every size can be 6/1000ths of an inch. So if oftentimes if they're too large, they can be they can fail. And so we're going to look at that now. So we're looking at it in the context of thin walls. So what we've done here is we've put a CAD file together that has a 2-inch tall wall, and we printed it at varying thicknesses, right? So the one on the far right, as it's CADed up, should be 0.1 mil. And they progressively get larger up to 1 mil on the far left, right, or 40/1000ths of an inch. And so what we really wanted to test here is, what is the ratio of thickness to height that you can reasonably achieve with your part designs and expect success in the DMLS process. So if you look on the far right in the picture of the actual part as it printed. So what you can see is the thinnest wall, right, which was 6/1000ths of an inch. Right, it made it up about 1/4 of an inch before it started to warp, right? And if it's too thin, as it gets taller, it's going to have stresses, and that stresses is going to cause it to move. Well, the second that it moves and it warps, the layers above it have nothing to adhere to. And so from that point forward, you're going to have a wall that's stunted, and the laser will continue to draw away. It's just going to draw away bits that get swept away by that recorder blade. And so that's what happened on the far right. It was too thin, it warped, and those subsequent layers had nothing to adhere to. And so, it failed, right? And if you look at the one right to the left of it, right, that's 0.25 mils, about 10/1000ths of an inch. It made it a little bit further, but again, not very far. And you can see it progressively goes on. Now, 0.75 mils, 30/1000ths of an inch, that built the whole way, but you can see the warp in it, right? The warp and the damage. So I would argue we're probably a little bit lucky that one actually completed the build. And so it was the one that was 1 mil, 40/1000ths of an inch, that was able to build successfully without any kind of warping or damage. So that gives us a design guideline to say, if you're designing parts for the DMLS process, you really should be focused on a 40:1 height to width ratio. And so if you can achieve that height to wall thickness, you're going to have really a pretty good chance of success of build on that. Now, the other thing to do is to eliminate freestanding features altogether if you can, or to brace them if need be, if they're going to be inside of this design guideline. Yeah, I think we'll have Q&A at the end. All right, the next thing that I want to talk about is surface roughness. Now, this is a huge limitation of the process. So folks that are first getting initiated with DMLS and they look at it, they're really kind of shocked at how rough the surface can be. So by measure, they're typically 200 to 400 micro-inch RA. And so, it's basically, often we tell people it's sort of like a cast part that's coming off these machines and printers. Now, the surface roughness really does vary. It varies by the material, it varies by the layer thickness, and it really varies by orientation. So now you can adjust it by parameter, right? So we can adjust the laser power and the laser speed, and we can achieve better surface finish. But then you're making other trade-offs, right, of your mechanical properties and the porosity and the build speed, right? So, oftentimes it's very difficult to really get to what you're hoping to achieve, which is sort of machine-typed surface finishes without secondary operations. But again, machining, post-machining, or post-polishing, that adds cost. Not every feature may be accessible. And so there's a lot of consideration. So DMLS, yes, you can orient your way around the process, you can post-polish, but you have to recognize that you're going to get a bit of a rougher surface than what historically you'd seen. So this chart shows kind of what the different surface finishes you can reasonably expect. So the bottom half of the chart was printed in a thinner layer thickness. That's better. So if you print in thinner layers, you're going to get better surface finish. And then if you look at which orientations within a part provide the better surface finish, your vertical sidewalls will always be your cleanest surfaces. And then your down-facing surfaces will always be the roughest. So an angled down-facing surface is going to have, fairly fairly tough. So if you think about it from the previous slide, right, your angle down, well, I don't have my, so the one right by the first finger, right, so your angled down facing surface is going to have the roughest, right? Your sidewalls, your vertical sidewalls will have the cleanest, and then followed by kind of your up facing surfaces. Okay, support removal. So, goodness gracious. All right, so DMLS is a supported process. So for those of you that are new to it, it definitely has supports on it. Unlike selective laser sintering, which is also powder-based and doesn't require supports, DMLS does. And it does for two reasons. One is it does start with a blank build plate, so you're printing these parts off of a build plate, and so we need the support structures to hold it to the plate. So we connect it with the plate and then cut them off later. The second reason you need them is warping. So you know, each layer is heated and melted very rapidly. That creates an extreme amount of stress in this process. And naturally what the parts want to do is curl. So we looked at those wall parts and they were really bending and flexing, and that was kind of what was going on. And these parts are so much stress, that's what these parts want to do. They literally want to curl up like a potato chip, you know, in a deep fry. You know, when you've heated them really tight and then, you know, really quickly and then pull them out. I mean, that's the amount of stress that's going on. And so, you know, if you have thicker cross sections, you know, that typically requires even more supports, and we'll get into that in a few slides. So you can see, you know, the picture here, the build plate in the little colored CAD. The gray is the build plate. The supports then connect it, and then there are supports. Any freestanding features within the part itself require to be supported. And the image on the right is a part with supports on it. So there's a significant amount of supports that go into this process. And you know, the other thing to keep in mind is, you know, every time the laser is drawing, this is a relatively slow process. And so the more supports you have, the longer it's going to take to build, the more cost and time we're adding. All right, so when getting rid of the supports, and you can see here that the images, so the one on the left of the image is the final part. The one on the right is the supported image. So this one was obviously built on a tilted angle. You know, we'll use CNC, we'll use a lathe, EDM, anything can help with the post-processing of the part removal. A lot of the support removal, to be honest, is very manual. So we've got a team of folks that are, you know, they're using Dremel tools and polishers, and that's how we're getting the supports off and grinding stuff down. I mean, this is wrought metal on metal, so there's no real easy way to do this. So the more supports that you can design out, you know, the better off overall you're going to be. So either designing minimally supported parts or self-supporting parts is going to be the way to do this. All right, so let's jump into some of the design considerations. Now we talked about internal features themselves, and so, you know, this is one of the major benefits of metal laser sintering, that organic and complex design. Now it can't be done though, you know, you have to be cautious as you approach these. So as we approach things like overhang, self-supporting features, bridges and angles, all of those have to be taken into account. Now we talked earlier too around internal channels and removing material itself with lattice structures. Now the trick there is, you know, hollowing out objects and replacing those voids. That's fantastic, but it has to be accessible to remove the powder, or we're going to have to tap a hole to knock some powder out. And internal channels, you know, the same. But if you can remove the time, the weight, and build, it'll build overall with less internal stress. So there's a lot of reasons to remove that weight. You just have to be cautious about the powder and the powder removal. All right, so one of those internal features that's really, really important when we're talking about self-supporting elements within DMLS is self-supporting angles. So here what we did is, you can see on the CAD in the upper left, that's what we're intending to build. Now we built that at a series of decreasing angles. And what you can see is, you know, the lower the angle, the less likely the part is to be able to support itself. So, you know, the angle relative to the build plate is going to be really important. As it gets more and more vertical, it starts to behave essentially like an overhang. And so this value changes you know, depending on the material, depending, as we talked, you know, a couple slides ago, depending on the orientation. But the concept remains the same. As the angle gets lower, you know, the surface roughness is going to get really, really rough. Eventually, it's going to fail. So as we look at these parts, and we've talked to, you know, our customers, our recommendation is that 45 degrees is a really good number. If you look at these parts, you know, once you start getting in 40 degrees, certainly down into 30 degrees, and you can see you can just get total build fail at 25 and less. So this is just a good rule of thumb that, you know, 45 degrees or higher is going to be a self-supporting angle. And if you can design those into your parts that you're intending for DMLS, you can remove a lot of that support structure and a lot of that time and cost. Like I said, if it gets too sharp of an angle, essentially it starts behaving like an overhang. So we'll look at that next. So this is, again, as you can see, you know, the CAD in the upper right. What we're intending to do was show sort of progressively longer overhang. So, you know, obviously an overhang, you know, any abrupt change in the geometry, and if you compare that to sort of those gradual angles that were self-supporting in the previous slide, you know, overhangs are very common and they're critical. Now, what you can see though is you start getting damage. DMLS is not very forgiving. It does not have a good allowance for overhangs, unlike some other processes in 3D printing. You know, because of the violence and the melting and stress, you know, it's got limited capability. And so, you know, we start to see damage on any surface, you know, less than 0.5 mils. So 20 thou an inch or less is really the allowable overhang. As you get above that, as you can look on the chart there, you start getting into a mil, 1.25 mil, you know, you get total build failure. So our rule of thumb is that you really should design in, you know, 20 thousandths of an inch or less overhang feature on your parts. Otherwise, they're not going to be, they're going to require supports, and you'll be adding cost. All right, so we talked a lot too around channels and holes. Are a great use of the technology. You know, we mentioned, you know, regenerative cooling channels, you know, conformal cooling channels. There's a lot of applications for internal design and complexity. Now, you know, being able to create those with freedom too, right? So you don't have to tap in and get very harsh angles. I mean, they can be very organic in their flow and structure. So that's a huge advantage of the technology. Now, the problem is the diameter of those internal channels increases. That top-facing surface of your the top-facing diameter starts to act like an overhang. And so unsupported holes larger than 8 mils. Now, something happened with my slides here because all of my dimensions have gone away. But looking from right to left, they basically go up from 1, 2, 3, 4, 5 mils. The largest is 15 mils here. And so if you look at the zoom in, which is 15 mils and 12 mils, you can see that top-facing surface of the internal channel, and it's truly acting like an overhang that we talked about a couple slides ago. And so you're getting that down-facing damage, you know, really where it can't support itself. And so until those self-supporting angles on the outer diameter come up and meet, you get build fail on the internal diameter of the part. And so that's kind of what's going on. And so really unsupported holes that are larger than 8 millimeters, they're going to suffer that down-facing distortion and that curl. So the tip is, and we'll show you, you know, in a little bit, if you use a teardrop, which is in essence, you know, 2 self-supporting angles to achieve an internal geometry, those will be self-supporting. You won't require supports at all, and you can avoid this whole thing. So for larger diameter channels, you know, smaller. So if it's smaller than 8 millimeters, you can go ahead and run them in a circular diameter. But if they're larger than that, using a diamond shape or a teardrop type shape will allow you to achieve what you're looking for with your part, but in an unsupported manner. So you can have internal channels really in any diameter you wish. Bridges is the next thing we're going to talk about. So if you look at, you know, obviously a bridge, any flat facing, you know, down facing surface, you know, that's supported really by 2 or more features, right? So as you look at this, again, we've designed it in with larger and larger width within the bridge. And, you know, the stresses here create some of the challenges. So the minimum allowable distance of an unsupported bridge is really about this 2 millimeters. So again, you can see in the lower left is the part actually built. At 1 millimeter and 2 millimeter, you're okay. Once the span starts getting above that into 3, 4, and 5 millimeter, again, you've got an unsupported down-facing surface that's too far. The stresses involved cause it to fail. Now, this is actually a really unique geometry as well, because it talks about another element of stress within this process, and that's really large cross-sectional areas. So you can see that when the bottom edge of the bridge surface came into the part, it pulled all of those legs inward, right? So this was actually designed to be vertical, vertical faces. But all of that, when that cross-sectional change came in, it literally pulled in all those legs. Now, in this case, we could solve that by flipping the geometry over, right, and printing progressively smaller cross-sectional changes. But that's not always possible, right? So sometimes, the orientation of the part, or you've got multiple areas that have wide cross-sectional changes. The other thing that we could do here is, instead of building vertical bridges, you could build in arches, right, that have more gradual change. However, at the end of the day, we're facing with extremely big stresses in this process, and that's just the nature of the process, which is why we need those supports. So what we're trying to show on this slide here is some of those big changes in cross-section and how much stress. So this part literally tore away from the build plate. So sometimes if you've got a bad start position within the machine and the build prep, that can lead to some weak adhesion on the plate. That wasn't the case here. This was a large part that literally tore itself up off the plate. Now we've seen parts that can warp even a 1-inch build plate. So that thick of a build plate of steel, just warp it. There's that much stress and pull involved in this process. Now, interestingly, oftentimes people think of a very simple geometry like a cube. Well, a cube, just a solid cube in DMLS, is actually a relatively challenging part because of these factors. There's just, you'll get a lot of warp and distortion trying to successfully build that. So it's really interesting. So the other design tip here is really try and limit major cross-sectional changes that come in, and try and do gradual transitions if and when possible within your designs. All right, so those are some of the limitations. Let's talk about some of the design and how we can bring this kind of all together. What we're talking about here is so this is just an example that we put together, right? So we didn't build this part, but we designed it up just to kind of talk about how all of that comes together, and to give you an example so you can see what the support strategy would be. So this would be conventionally made. It would be a 3-part assembly. You got a coiled tube in the middle, and then 2 components with large flanges that you'd want to be using to assemble them up. So in this case, on the far right would be how we'd have to design and prep for this. We didn't make any changes to it. It's designed as it came in. And so as you look at that, the number of supports required for this to successfully build it would be astronomical. Supports they're literally everywhere. They're inside the part. It would kill any functionality of the part. They're not accessible. So there would be really no way to print this. So the first thing that we would look at doing is kind of revising this. So let's take advantage of removing some of the unnecessary components, and let's start by doing that. So we went back. We asked the designer, hypothetically, right, to get rid of those flanges. So now we're starting to accomplish some of those goals that we talked about in terms of reducing weight, reducing assembly, reducing labor. But in this case, the number of supports needed would still be prohibitive, right? It's still going to destroy the functionality. It's going to add a ton of that build time. It's going to add cost. So we also have some very flat surfaces coming in, right, with those big changes in cross-sectional, and that's going to probably lead to some warping and some build failure issues. So now let's start at revision 3. Revision 3 is we've abandoned any kind of need to make this conventionally, right? And so we're really designing with DMLS in mind. And in that case, we've taken this into a more teardrop. So we've taken those flanges and we've designed them as a self-supporting teardrop. We've got self-supporting shapes. We have no supports because they're all diamond and teardrop in the interior anymore. So the outer parts are self-supporting. The internal channels are self-supporting. We literally have one row of supports that go along the bottom, and that's all that would be required in this part. And so it'd be easily removed from the build plate. It would be minimal amount of prep, and overall we'd have a lot better part that would likely see a lot of savings compared to the traditionally manufactured part. All right, so real world. So that's kind of a hypothetical. Here's a very real world of that. So this is the University of Minnesota. Their aerospace students were looking to achieve a 3D printed rocket engine. And when they first started doing this, they were literally using machined parts and off-the-shelf pipes. And that's kind of how they were doing this. So they were doing a lot of machining themselves, a lot of tooling, a lot of work. Now, that's common, right? They're students, so they're being scrappy. I applaud them for that. They approached us, so they got a grant, they approached us. And what they really wanted to do was do a regenerative cooling. And so that was going to allow them, rather than carrying all the extra weight of some sort of cooling function, on the rocket, by adding coils that progressively decreased around the exterior of this, they were able to eliminate a lot of weight off of their rocket, but they knew that they couldn't really do that conventionally, and so that's what they were looking to us to do. The other thing is they were trying to balance, the rigidity of that outer wall that obviously is going through hot fire testing and a lot of stress, with the transferability of a thinner wall, and so they were really wanting to iterate this a few different times. And so they didn't want to, commit to any kind of traditional manufacturing until they had the design dialed in. So really the only way to do all of that was with 3D printing, especially for an engine of this size. The final component was really only 6 pounds, and so this is relatively small in an aerospace context. So one of the things that we did with them, if you look at their initial part, we worked with them really, so they had a lot of really tight angles or harsh angles in it on their initial design for 3D. You can see they had a lot of circular design, so they used everything in a circular manner. And so the first thing we did was move things into that teardrop shape and eliminate a lot of the self-supporting. They also had some pretty harsh or tight angles in there, and so we converted that into the 45 degrees so it would be self-supporting. And ultimately, this removes a ton of time. It removes, all of that cost and weight. Now, it's supposedly this winter is when this semester is when they're going to get together and actually fire this. But we printed this engine. It's in their hands. They've done some initial testing, so we're excited about this. But this is sort of a real-world example of what you're able to achieve in 3D printing. That historically we weren't able to achieve at all. So I'll wrap up here. We got about a little over 20 minutes left. I'll take a couple minutes here to wrap up, and then we'll open it up for questions. We've talked a lot in this presentation about parts that are ultimately meant for production, within DMLS. But DMLS is also, it's really great for prototyping, especially smaller parts. They tend to be, fairly quick. We can produce DMLS parts in standard, lead time of 3 days, for smaller parts. They're generally really, cost effective and quick turnaround. And so you can achieve a lot of design iterations, within your launch window, or shorten your launch window and get to market faster. Typically with larger, bulkier parts, prototyping may be a bit more of a challenge. It may not make sense unless you're looking to unlock significant time savings, or your material costs themselves are cost prohibitive. We've got a lot of examples with customers that have extremely expensive materials, and if they're using machining, you're leaving as much money on the floor in chips as you are, in the part itself. And so there are certain areas where DMLS may make a lot of sense. So depending on the part, depending on where you're at in your project, we would really encourage you to think about DMLS both for prototyping, and for end-use parts. As we talked about, these are end-use materials. They're highly functional. You can get really complex and precise geometries out of them. And because they're wrought alloys in their performance, you can use them for functional testing. There's a lot of 3D printing technologies that are great for form and fit, but don't really have functional grade materials. DMLS is not one of them. So, it's great to use, and it can always be, make sure your design is transitionable into your end manufacturing process, as opposed to, designing it for 3D printing and being stuck there. So, make sure you're aware of kind of how you ultimately want to build this. So, wrapping it up, DMLS, it opens up a lot of design opportunity. It's not going to replace traditional manufacturing methods. It's one more tool for you to use within your toolkit as you're looking to designing your parts and achieving value, and saving money overall. So, understanding the constraints of the process itself with the support structures, with the overhangs, with some of those internal features. That's going to be critical for you to successfully, achieve the value that you're looking to within DMLS. So I will hit pause here and open it up for questions.
Hello.
Oh, there you go.
Thanks, Dave. I know that you mentioned that this is usually used for prototyping. I would say in the next 5 to 10 years, do you think companies will be using this more on the production side at all?
Yeah, when I mentioned that, I mean that's today, where a lot of people are using it for prototyping. I would say the majority of the growth and interest that we're seeing in metals printing is around end use or production parts. There's a lot of interest in that because you can get such complex designs, because they're engineering grade materials. Production is going to be the growth engine for metals. Quite candidly, we've talked here a lot about DMLS. There's a lot of innovation and new technologies that are emerging to increase the build speeds, to achieve even finer feature resolution. And so I think DMLS will continue to be a really desired technology. There will be others, and more and more and more people will use these beyond prototyping in as an end-use manufacturing technology in and of itself.
Can temperature annealing decrease the stresses in the part successfully?
Can annealing decrease this? No, they have to go through, you can use annealing as a post-process. Once they come off the printer, we have to put them through a stress relief cycle in an oven for multiple hours, depending on the alloy. So you can't just anneal them. You have to take them through a full stress relief cycle. And in certain cases, they've got to go through a more aggressive stress relief, depending on what the application of the part is.
So you do that? Then.
Yeah. So our typical process, once they come off the printer, the first thing we do is stress relieve them before we remove them from the plate. If we hadn't done that, they would literally spring off the plate and immediately warp. We have to relieve that stress out of the part before we even remove them off the build plate, and at that point they're handleable.
Hello. The same kind of adding upon her point, saying the large-scale production for additive manufacturing applications. What is the economics of that comparison between the additive manufacturing and the traditional manufacturing? Like you touched upon a few items saying that it does, for additive manufacturing, it removes the assembly line. You have, instead of several components, you're printing out one single component. It's kind of saves time and cost at a certain level. But what are the other competing aspects as far as economics is concerned for making additive manufacturing competitive for large-scale production?
So is the spirit of your question about like repeatability and reliability within 3D printing?
Yeah, including all of this, the economics on a broader scale.
Yeah, I think the control and the tolerances of the technology itself actually are fairly well known. There are industries today that are using metal printing for highly complex parts. So if you think about one of the most common applications in end-use parts today is in the medical industry with implantable devices, often using titanium. Those parts are often highly customized to the individual patient and require fairly stringent, tolerances. So when we're talking some of the generic tolerances in the prototyping, where you've got a whole range of geometries, that's a little bit more challenging to kind of offer up a guideline on that. When we've worked with a customer to dial in their part and have it designed for the process, we'll take all the orientation into account, we'll take the support strategy into account, and we'll eliminate as many variables as we can, to the extent of, if it's desired, using a single lot of powder, printing off the same machine with the same orientation out the same build plate. So there are ways to achieve high repeatability and reliability out of DMLS, not to the tolerances that traditional CNC machining can achieve as built, but there are secondary operations that can help deal with that. So we can always post-machine the part to achieve, within a thou, plus or minus, or even tighter. If there's a key feature or a mating surface where the surface roughness, would preclude use otherwise.
So how about the economics of it on large-scale production? How does it play out?
Yeah, the economics, now that is the more interesting challenge, right? So, as we mentioned earlier, right, the economics of metal printing, if it is a one-for-one component, right, where it can be machined or it can be, metal injection molded, DMLS is going to be cost prohibitive. So unless the count is extremely low, like in a prototyping scenario where you're talking one to 5 parts, DMLS is not going to be your most cost-effective solution. Where it can be your most cost-effective solution is if you're designing in optimum part performance, you're removing weight or you're removing assemblies. In other words, you're capturing value in other areas of your production chain, not in the direct part-to-part component. So, an example, consumer products that have millions and millions of units in metal or in just traditional plastic injection molding. By printing a mold that has an internal conformal cooling, they can reduce the cycle time, by seconds. Now, seconds in their world is a lot of money because they're running so many parts coming off and so many cycles per day. And so that's why we really ask people to focus on those design goals and what you're trying to achieve with DMLS. A lot of times, the first conversation between us and a customer will be a CAD file, and we'll look at it and we'll be like, MIM part. And we'll have to have that education of what they're trying to achieve and what they really hope, to leverage in DMLS broadly, either new process or new design. Otherwise, it won't be the most cost-effective solution. So that's why we say it's not going to replace traditional manufacturing. It's one other choice of technology within the broader set. So the question is there no way to use alternate support materials or some sort of hybrid technology? Is that?
Yes, that's right. Or pre-prepare support material, like put that on the bed and then work on top of that.
Within DMLS, no, right? Because being able to control the layer thickness and pre-plan where the support material will be, that's an active process. So you got a recoater blade that's pushing powder around. So to be able to control the powder in the mix, I think that would be very challenging. Now that said, there's a lot of innovation, as I mentioned. Now, one of the areas of innovation that people are looking at is, the support strategy. So at Rapid, a few months ago, Desktop Metal was all the rage. They were a huge sponsor of Rapid, and one of the things that they're looking to do is lay down a layer of ceramic. So the support material itself is the wrought alloy, and you need that because of all the stresses involved. You can't have kind of a ceramic trying to hold down, a stainless steel part. That's not going to be effective. But what they can do is lay a thin layer of ceramic between the support layers and the part layers for much easier removal. So now, but that's one that goes through a debinding step and a sintering step. And so in doing that, right, you burn a lot of that ceramic off, and you create, a micro space in between that you can clip the supports off. In this DMLS process right now, that's not achievable. But I think the industry as a whole is really looking at how do we make the materials less expensive, how do we make the machines run faster, and how do we eliminate the labor that's involved in the process. And so, the answer that I give you today may not be the answer that I'd give you in a year, and it certainly won't be the answer that I give you in 2 years.
Touching upon the same earlier question, you said that if you are printing out a typical component that you can actually CNC machine or cast it out, you said the cost is prohibitive. So this cost, can you explain which components of the printing part adds to this cost, and how do you see these parameters changing over time with technology?
Yeah, there are two primary drivers of the cost. So one is the powders themselves. They're very expensive. The other is the machine time. And so, these machines are extremely large, they're extremely expensive, and it's the laser draw hours. So when the laser is drawing, it's adding cost. So with other 3D printing technologies, we track what we call recoat time as opposed to draw time. Most of the other technologies is roughly, 50-50. It takes a long time to kind of recoat the layer. Now, it takes a while to recoat it here. But because this is such a violent process, the speed at which you can actually draw the laser is much slower than what you can in some of the other 3D printing technologies. And so, both literally the time that it takes to draw out each layer of the part is what's adding a significant amount of cost. And as I mentioned, the powders themselves. So, if you think about MIM powders that have, huge demand, and huge supply, those costs are relatively reasonable. These are very specialized, or generally specialized powders, because of the parameters that they're developed for. So, how those are going to be controlled in the future, I think, people are looking at how do we make the machines print faster to achieve the same results, and get the build times down. Most of the new technologies are operating, as they are in the plastics, under open platforms. So if you think about all of HP's announcements around the multi-jet fusion technology, open platform. Formlabs, relatively open platform on desktop. And even Desktop Metal, an open platform. And part of what they're trying to achieve there is to get more engineers doing, the material engineering, the material science, and having more options available within the materials side that will drive those prices down. Desktop Metal has gone so far as to say, part of the reason why they absolutely want to use the powders they do, MIM-based powders, is to get that pricing down. So, as I think about the additive manufacturer user group, the AMUG, and Rapid, most of the conversation in the 3D printing industry is how do we get 3D printing from where it historically has been in prototyping and into this end-use production. And to do that, on the plastic side, we got to get the mechanical properties improved and not have mimic or ABS-like materials. And on the metal side, we got to get the cost down.
Yeah, I have another quick question. In the design for manufacturing, one of the strongest component is the computational tools that you can use to kind of optimize your support structure design or the design itself for the specific manufacturing. What is your comment about what are the capabilities today, and how much are they economically feasible right now to design a product for a manufacturing application?
as far as being able to achieve cost effectiveness with DMLS?
Yes, and in the sense, yes, that is true. And I'm talking about the computational tools that are available. Are they, what are their capabilities, and how far are they able to help someone to build, design a product for a specific manufacturing?
As far as software tools, they're relatively limited. I really think a lot of that expertise rests within the equipment manufacturers, or us as service bureaus. And that's part of a lot of the value that we add, is providing that design for manufacturability feedback. So we have a team of applications engineers that look at every part. They're assessing those parts. They're offering that feedback as to how you can reduce the build time, create self-supporting features. We offer sort of those guidelines, some of the challenge areas that may exist within the part. I think over time, one of the things that we've seen is more and more people having better design for their parts as people get more familiar with 3D printing and really start engineering and designing towards it. I think the real trick is having a clear understanding up front of can you achieve your desired goals in 3D printing and design for that as your manufacturing process, or do you want 3D printing to support your design and development process with a traditional manufacturing step at the end? Because the design goals will be distinctly different between the two. And so really operating with that end manufacturing in mind as you design for 3D printing is really what's critical.
Okay, any other questions? Anybody? Any other questions? Okay, well, let's hear it for Greg Thompson and Proto Labs for sponsoring today's Brew and View. Thanks.
Yeah. So I'll leave you with this. If you would like some of that feedback, so please do go to our website. It's it's an instant online quote, so you can upload your CAD file. You can play around with the orientation and your quantity, and we'll give you the price. You can also select to have a manual quote where you have a conversation with one of those applications engineers. So please do swing by our booth. We're down at 723. We'd happy to have more conversations with you and answer any questions you got.